Welcome to Study Loop.
In this question, we are provided with two preliminary equilibrium reactions that I'm going to label 1 and 2 first. And we are also given their equilibrium constants. So I've labeled them Kc1 and Kc2, unlike in the question, so I can distinguish between them. And then we are also given a third equilibrium reaction, which is pretty much what we get from subtracting the second reaction from the first. So if we did 1 minus 2, we get 3, which is this. So we are asked to calculate the Kc for the third reaction. So we can just go over the reactions to get a better understanding. And the first reaction is showing us the reduction of cobalt oxide with hydrogen to produce cobalt and water, while the second reaction is showing the reaction of hydrogen with carbon dioxide to produce carbon monoxide and water. So like I said again, if we subtract 2 from 1, we get 3. So 1 minus 2 is equal to 3, which is the third reaction given in the question, and that shows the reduction of cobalt oxide by carbon monoxide to form cobalt and carbon dioxide. And we are asked to calculate Kc3, which is the equilibrium constant for the third reaction. So because we know that we get the third reaction from 1 minus 2, we can translate that and determine that we have to divide Kc1 by Kc2 to get the value of Kc3. So if you need to subtract the reactions to get the new reaction, you divide the Kc values to get the equilibrium constant for the new reaction. So this gives us a value of 4.8 times 10 to the power 2. So this is from 67 divided by 0.14. Kc3 is this. So if we move on to the second part of the question, the B part of the question, this is the answer to the A part. And if we move on to the B part of the question, we are asked to determine if carbon monoxide is a stronger reducing agent or a weaker reducing agent compared to hydrogen at 823 Kelvin. So what we have to do is compare the two equilibrium constants for the reactions that are discussed in the question. So the reaction 1 and the reaction 3. So if we compare the Kc values, we see that Kc3, which is 4.8 times 10 to the power 2, is much larger than Kc1. So this tells us that the third reaction is much more preferable, or the forward reaction of the third reaction is more preferable than the forward reaction of the first reaction. So the forward reaction of the third reaction is the reduction of cobalt oxide using carbon monoxide, and the forward reaction of the first reaction is the reduction of cobalt oxide using hydrogen. So if the reduction of cobalt oxide using carbon monoxide is more preferable, it means that carbon monoxide is a better reducing agent compared to hydrogen. So carbon monoxide is a better reducing agent compared to hydrogen. This is derived from the fact that Kc3 is much larger than Kc1. It doesn't need to be much larger. Even if it's slightly larger, it still means that carbon monoxide is a better reducing agent compared to hydrogen. In the third part, we are asked to do a calculation, and we're told that someone took a sealed tube and placed 5.00 grams of cobalt oxide solid in it, and then pumped some carbon monoxide gas into it until the pressure of the vessel rise to 1.00 atm, and the temperature was 298 Kelvin, while the volume of the vessel is 250 milliliters or 0.25 liters. And assuming these things, we are asked to calculate the concentration of CO gas in the tube. So the tube has a small amount of cobalt oxide in it, which is 5 grams, and then there's also carbon monoxide in it, and it's sealed, and it has a pressure and a temperature and a volume that's provided. So we can assume that carbon monoxide acts as a ideal gas here, and that there is no reaction occurring between carbon monoxide and cobalt oxide solid at this temperature, which is said in the question, and we can calculate the concentration of CO gas in this tube. So to do that, we have to use the ideal gas law, which is PV equal nRT. So if we calculate N using this, N is going to be equal to PV divided by RT, and this is N of the carbon monoxide. Sorry about that. Carbon monoxide N, and that will be equal to 1.00 atm times 298. I'm sorry about that. It has to be V, not T. I mixed up T there. So it has to be 0.25 liters up there, because we are substituting for the values in this equation right here. And we have to divide this by the R value with the appropriate units, which is 0.082, and that is atm liter per mole and per Kelvin. And we have to multiply this by the temperature, which is 298 Kelvin. So once we cancel out the units, atm for atm, liters for liters, Kelvin for Kelvin, we get a number of moles of, sorry about that, CO gas, and that's going to be equal to 0.01 moles. And we are asked to calculate the concentration of CO gas. So what we need is N divided by V for CO gas, and that will be equal to 0.01 moles divided by 0.25 liters. and this is equal to 0.04 moles per liter. This is the concentration of CO gas present in the tube at 298 Kelvin and 1 atm pressure. And then in the next part of the question, we are asked to calculate the remaining cobalt oxide solid, assuming that someone heated the tube to a temperature of 823 Kelvin, where reaction 3 can take place and cobalt oxide reacts with carbon monoxide to form cobalt and carbon dioxide. So we can calculate the number of moles of initial cobalt oxide from the 5 grams that were inserted into this tube. So initial CO oxide solid or cobalt oxide solid is equal to the mass 5 grams divided by the molecular mass of that, which is 74.9326 grams per mole. So the gram units cancel out each other, and you get from this 0.06 moles. So this was the number of initial cobalt oxide moles present in this vessel. And then we can also calculate the number of moles of CO present initially. Actually, we already calculated that, and that is equal to this 0.01 moles. So CO is going to be the limiting reagent in this system, 0.01 moles, and because the stoichiometry between cobalt oxide solid and carbon monoxide gas is equal to 1:1, the same amount of cobalt oxide gas moles present will react with the number of carbon monoxide moles present. So I was talking about cobalt oxide solid. So they will react with each other in a 1:1 stoichiometry. So 0.01 moles of cobalt oxide will react with the present 0.01 moles of carbon monoxide. And so the remaining moles of cobalt oxide solid, remaining CO oxide solid is going to be equal to 0.06 minus 0.01, and that is equal to 0.05 moles. And then what we can do is determine the remaining mass of cobalt oxide. And to do that, we just have to multiply 0.05 moles by the molecular mass of cobalt oxide, grams per moles units. The per mole unit will cancel the mole units. And we discussed what the molecular mass was for cobalt oxide before. It's this, 74.9326. And if we do that, we get the final answer of 3.75 grams. So out of the 5 grams, there's going to be 3.75 grams of cobalt oxide remaining after it interacts with the CO moles that were present in the vessel. And this is the answer to part D.